Okay, we will go through some important points in the class 12 physics chapter 10 wave optics. Okay, some of these points you already seen in chapter 9 ray optics. How light bends when it travels from rarer to denser and denser to rarer medium. So chapter 9 it is ray optic. This is the wave nature of the light. In this chapter we will study the wave nature of the light. Huygens principle. Okay, this is important. This is Huygens principle. First you have to know what is wave front. Okay. Mm, Space, they are the points which oscillate in space, in phase, same phase. Okay, these are the wavelets oscillate in same phase called wave front. Thus the wave front is defined on the as a surface of constant phase. Okay, this circle is a wave front. This has the constant phase, all these oscillating at the constant space. Okay, the energy of the wave front is perpendicular to its direction. Okay, this is wave front is going in this direction, so this perpendicular to that is the energy of the wave travels in a direction perpendicular to the wave front. Okay, so now when we look at the wave front, the light from a far away object like sun, this spherical wave front will look like a plane wave from sun to earth, so many millions of kilometers it travels, so it look like a plane wave like this. Okay, as a large at a large distance from a source, a small portion of the sphere can be considered as a plane. Okay, like this a plane wave. Okay, so this wave front is a spherical thing, but because it is coming from a large distance like sun, so I can consider as a plane wave. So this is what Huygens principle. Okay, so what it says, each wave front is considered of a secondary wavelet, small like this. Okay, infinite number of the secondary wavelets which is oscillating. Okay, then if you draw a common tangent to all this envelope, then the new wave front is formed. Okay, so this is the term wavelet. So in the wave front, each point is called a wavelet, oscillating wavelet. Okay, and this wave front is moving in the forward only. From this wavelet, this next wave front is moving forward only, not backward. That is what Huygens principle says. Okay, according to the Huygens principle, each point of a wave front is a source of secondary disturbance and the wavelets. Okay, here you see wavelets emerging from these points, spread out in all directions with the speed of the wave. Okay, now we have to draw the envelope and you see the new wave. That is very important. You see what is the from this point, the new wave front at time t, this is at t equal to 0. From this oscillation due to this wavelet, the new wave front at time t, the radius of this is vt. Okay, sphere of radius vt. V is the velocity of the wave and tau is the time. Okay, at after 1 second or 2 second like that. So what will be the new wave front? Then you have to draw the circle of the sphere of this radius, then join the tangent of the tangents of all these things, common tangent to all these spheres. Okay, this is important. You have to draw the common tangent to all these spheres, then you will get the new wave front. So So it is moving in the forward direction only, that is important. Okay, and 0 in the backward, that is important. Okay, these wave fronts moving in the forward direction only. See this refraction reflection of the wave. See how they are drawing this wave. In the last chapter 9 they drawn the ray. Okay, so you have to see the difference between how they draw the wave front, how wave front is drawn, how a ray is drawn. So the speed of the light wave depends on the medium. Okay, denser medium, speed of the light is lesser than in the vacuum. So this is very important. Whenever there is a change in medium, the frequency is not affected. So only the other things will change. Speed and the speed will change, but not the frequency. The above equation implies that when a wave gets refracted into the denser medium, the wavelength and the speed of propagation decrease. Okay, wavelength speed decrease, but the frequency is not changed, remains same. That is important. Whenever there is a change in medium, frequency is not changing, light frequency. Okay. So this critical angle last chapter also we have covered, is same applies here. Only thing is that you have to use the waveform, not ray form. Okay, this is after passing through the prism, lens and the mirror. A monochromatic light. Monochromatic means a single wavelength. The light has only one wavelength. Okay, is incident on a surface separating two media. Okay, the reflected and refracted light both have the same frequency. Okay, that is what frequency won't change whenever there is a reflection and refraction. They are asking why. Okay, solution: reflection refraction arise through the interaction of the incident light with the atomic constituents of the matter. So incident light actually interacts with the atoms. That is why refraction reflection occurs. Atoms may be viewed as oscillators, okay, which take up the frequency of the external agency light, causing the forced oscillations. The frequency of light emitted by a charged oscillator equals to the frequency of the oscillation. Okay, the frequency is equal to the observed frequency only. Thus the frequency of the scattered light equals to the frequency of the incident light. Okay, the atom level. So the light is observed by the atom and released also in the same frequency. When light travels from razor to tensor medium, the speed decreases. Okay, when light in the air is 3 into 10 power 8 meter per second, means in denser medium like glass and water it will be less than that. Does the reduction in speed imply reduction in the energy carried by the light wave? Okay, when the speed is reduced, means does the energy is reduced? Is it no? The energy carried by the wave depends on the amplitude of the wave, not the speed of the wave. Okay, the energy depends on the amplitude only, not on the speed of the wave. In the wave picture of light, the intensity of the light is determined by the square of the amplitude. Okay, amplitude square is the intensity. What determines the intensity of light in the photon picture of the light? Okay, so photon picture of the light they are asking. For a given frequency, the intensity of the photon picture is determined by the number of photons crossing an unit area per unit time. Okay, photons crossing per unit area per unit time. Okay, in this these waves from sources, interfering waves, there is a crust, the represented by the solid circle, represented by the dashed ones. Okay, crust and trough. So using superposition principle, the phase difference between the displacement produced by each of the waves does not change over the time. So what is a coherent wave? So the phase difference between these waves is constant and is not changing over the time. Okay, the phase is not changing over the time. Okay, that is coherent waves. These are the crust and trough. Okay, that is, I already told you what is crust and what is this is in the figure also. The solid circle crust and dashed trough. Okay, now if you take two light sources, the wave from this light source and this light source meet at this point. If they have they differ in the number of cycles, exact number of cycles, then the path difference will be in terms of lambda. Okay, n lambda, general form n lambda. Okay, so the phase difference will be 0 because one cycle is lambda. In terms of n lambda, the phase difference will be 0. Okay, but in this case, if it is not difference is not in terms of lambda, like it is 0.5 lambda, then phase difference will be 180. Okay, so this is in phase and this phase difference here will be 180 because it is not multiples of the lambda. Intensity is proportional to square of the amplitude. Okay, here you see that is important. Here lambda equal to 360 degree. Okay, 360 degree. One cycle is the lambda. Here they mention one cycle is lambda. One cycle is 360 degree. If they differ in multiple number of cycles, then phase difference will not be there. Only path difference will be there. This is the path difference, but there is no phase difference. Here there is a path difference, but phase difference of 180 degree. Okay, the path difference of 2 lambda corresponds to 4 pi. That is 1 lambda is 2 pi. 1 lambda equal to 360. That is degree 2 pi. 2 lambda means 4 pi. So path difference between phase difference. Okay. So here there is path difference of the lambdas. No phase difference here. Here path difference and phase difference is. So here when two light sources interact, when at the crust both are in phase and when both are in the coherent waves, they form the constructive interference. Okay, the bright spots, and this dark is they are not in phase and they differ even 180 degree. Then destructive interference, they form destructive interference. Okay, n plus half lambda, 1 lambda is 360, half lambda is 180 degree, so they differ by 180 degree. Destructive interference, this is constructive interference. This is bright spot, bright fringes, this is dark fringes. This is the general formula. Okay, destructive interference, constructive interference. This is for the incoherent waves. For the incoherent waves, rapidly changes with time. Okay, that is incoherent. This is Young's experiment, double slit experiment. This is the screen. These two are the light sources. Okay, in this screen there will be fringes formed, dark and bright and dark fringes based on whether it is constructive interference or destructive interference. Constructive interference happens this at a distance from here. Now, see, this is the distance from this. The distance is multiple of this n lambda d by d. This constructive interference will take place. That is, bright fringes will take place. But at this distance, that is n plus 1 by 2 lambda, at this distance there will be a destructive interference, that is dark fringes. Dark, these are destructive, bright is a constructive. Okay, so this is distance from the center. From the center, x is the distance from the center. At this distance there will be a constructive interference. At this distance there will be a destructive interference. Bright constructive, dark destructive. Okay, diffraction. The condition for the diffraction is the wavelength of the light should be comparable with the that slit width. Okay, wavelength. This is the slit width, means this width here. This light passing through that hole. Slit width. Okay, diffraction. Okay, wavelength of light is much smaller than the dimension. If wavelength of light is much smaller than the dimension of the most carrier, we do not encounter diffraction, so we can't see that light. Okay, so when the wavelength is comparable to the dimension d, then only you will see the diffraction. So why light bends on the corner in these edges is because of that Huygens principle, where we make the envelope of that wavelets. Yeah, that is tangent. At these edges it will be curved. The tangent will be curved. That is why turn around the corners. Okay, here single slit, the intensity will be maximum at the center and it goes on decreasing as we move from the center. Maximum at the center and decreasing. You can do the experiment with the blades only. Polarization. See the fast axis of the Polaroid. Okay, when the light is oriented in the fast axis of the Polaroid, the light will pass. See, whenever you pass a unpolarized light to a Polaroid, the output will be, the intensity of the output will be 50% of the original intensity. Okay, so the polarized sheet, it is observed that the intensity is reduced by half. Okay, when you pass a unpolarized light to a Polaroid, the output will be 50%, intensity of will 50% of the original intensity. So when you pass a polarized light to another Polaroid, then the intensity of the output will be based on this formula, that is Malu's formula. Okay, it depends on the angle between the pass axis of the Polaroids. Okay. See here, the all light will be passed. The pass axis of this these two are in parallel, so all light will be passed. Something will be is a complete block at 90 degree. Okay, no light will pass out of this. So this is completely passed, and this will be polarized in this. Okay, electric vector. So if you adjust the here, this is a parallel, all light will come out. uh, this from here, if you adjust this, you won't change, you won't see any change in the output intensity, okay, because the input is a unpolarized light, okay, here, okay, that is what they are saying. Adjust the angle between the polarized or the two. See, intensity coming out of the single polaroid is half of the incident intensity. By putting the second polaroid, the intensity can be further controlled, okay. Discuss the intensity of the transmitted light when polaroid sheet is rotated between the two crossed polarized. Two crossed polarized means their pass axis at 90 degree, no light will come out of the second polaroid, okay. Let I naught be the intensity of the polarized light, okay, that is after first polaroid, after passing through the first polaroid, okay. Then the intensity of the light after passing through the second, this is as per the Malu's law. Theta is the angle between the first polaroid and second polaroid, okay. When theta is the angle between the one, okay, or crossed angle, the pass axis of this will be, okay, pi by 2 minus theta, hence the intensity of the light, okay, is, okay, this is the summary. Okay, we will go through this exercise problem. A monochromatic light of wavelength is incident from air on the water surface, okay, rarer to denser wave. What are the wavelength, frequency and the speed of the reflected and reflected light? Refractive index of the water is 1.3. okay, this is the wavelength of the light. Nanometer they are given. Nanometer is 10 power minus 9 meter. Refractive index of water is given. So the incident medium, reflected medium will be same as the incident medium. So the frequency will not change. We already seen, okay. Frequency is not going to change. So the lambda, that is wavelength, is going to same, frequency will be same, velocity will be same, okay. So they are given lambda, so we can find the frequency. F equal to velocity of light in vacuum divided by the lambda. Lambda is this, so you will get the frequency. So frequency, velocity is in the air is going to be same, frequency is this, then lambda is not going to change, okay. Reflected ray lambda, C is same, F is this, okay. But after refraction, so the frequency is not going to change. So the frequency is, because when you change the medium, frequency is not going to change, but the velocity is going to change. The velocity of the depends on the refractive index, okay. So the refractive index of the water, so this is velocity of light in the vacuum divided by refractive index of the medium. So this is the velocity of light in the water, okay. So velocity is going to change, frequency is not going to change. So then that means the velocity of light is equal to f frequency in the wavelength. So the frequency is not going to change. That means from lambda, so this is the velocity is that frequency is this, frequency is not going to change. From that we find the lambda. What is the shape of the wavefront in each of the following cases? Light diverging from a point source, okay. Light diverging from a point source will be spherical only, okay. Light emerging out of the convex lens and a point source is placed at its focus, okay. Point source is placed at this focus. So that is at this focus. Okay, this will be plane wave front. Okay. The position of the wavefront of the light at a distance star into the wave. Okay, this is I already showed you. Whenever light comes from the far away, it is look spherical, will look like a plane. Okay, a plane wave because it is far away from the earth. The refracting index of the glass is given. What is the speed of light in the glass? Okay, speed of light in this glass, speed of light in the vacuum. So this divided by the refracting index will give the speed of light in the medium. Okay, velocity in the glass equal to speed of light in the vacuum they have given. Then divided by refracting index will give the speed of light in the glass. Okay, velocity is slower in the glass because it is denser medium. Is the speed of the light in glass independent of the color of light? No, that is it depends on the color because the wavelength varies. If not, which of the two colors, red or violet, travels? Okay, it is speed of light depends on the wavelength because its frequency is not going to change. The wavelength will change, so the speed varies. This has the smallest wavelength, red is the highest wavelength. So the speed of violet is slower than the red because this speed is the product of the frequency and the wavelength. Wavelength of the red is more, and where the violet is, so the violet will be slower. In Young's double slit experiment, the slits are separated by, okay, this is D, small d is given, and this is the capital D. The distance between the central bridge and the fourth is this, x is given for n equal to 4. Determine the wavelength of light. Okay, from direct formula you can find out. So this is the formula they are given, d, okay, and then the n also they are given 4. Then we have to find the lambda. Okay, substitute this and you will get the lambda. It's straightforward. In Young's double slit experiment, monochromatic light, that is monochromatic means single wavelength. Lambda intensity of light is at a point on the screen where the path difference they are given. Okay, in multiples of lambda, that means phase difference will be 0. Okay, path difference is in lambda means phase difference will be 0 in k unit. What is the intensity of light and the difference is this? So lambda by 3 means it is 1 lambda is 360 degree, 120 degree. Lambda means phase difference 0, lambda by 3 means there is a phase difference. Lambda 1, lambda 2, no, this is the intensity. Okay, intensity they have given, the phase difference is lambda by 3. Okay, lambda is 2 pi, lambda is 360 degree, that is 120 degree. Okay, so this is the intensity. So L equal to K when phi equal to 0, that is phase difference is 0, they are given lambda, that means that is phase difference is 0, this is K. Okay. So K equal to I naught. Okay, then the final intensity will be this K by 4. A beam of light consisting of two wavelengths. Okay, two wavelengths used to obtain the interference fringes. Okay, two wavelengths they are given. Find the distance of the third bright n equal to 3 on the screen from the central maximum from n equal to 0. They are asking wavelength. Okay, this is for the least distance. I are asking here 10.6. Okay, this formula is there in the book. Lambda 1 lambda 2 is given. Okay, for n equal to 3, this is the distance from the center fringe. Okay, this is this distance. See, least distance means between the successive periods only it will come. So between the successive period, so n minus 1 of lambda 1 and nth of lambda 2. Okay, because it is given, they are asking least distance, they are asking. Okay, so after substituting this you will get this. Okay, because D and D is not given, we are using that we are not, without substituting the values. Okay.